So I am at libEVM. I'm currently an engineer at Mantle. So if you guys want to build any bounties on Mantle, let me know. Our booth is just outside. Um, so yeah, today I want to talk about data analytics tools for Web3. There's a lot of flavors out there, but for more context about this talk, was the Paradigm had a Rust x Ethereum day in San Francisco a couple months ago. And they talk something about the data endgame, where everything is fast, everything is cheap, everything is effortless, and you can get any kind of data in any format for any hardware. So I thought that was very intriguing, and so I kind of went on this little rabbit hole on how to better extract data. I know the standard today is using the graph, or for example, extracting data through JSON RPC calls, and those are fine, those are good. It's just an issue when you want to do analysis on data that is more than 1,000 blocks old. It takes time, it takes effort, and it is not effortless. What we want is to be able to transform, extract and transform data effortlessly we want to be able to extract and transform large chunks of data effortlessly. And so today, after going down the rabbit hole, I'll be telling you what I've learned, and hopefully you will learn something new as well. So tools introduced. So we got Ref, a Rust-based EVM node. We got Cairo, which is another tool from Paradigm, which is a Rust-based data extraction tool. And also we got Polars, which actually isn't a tool, but it's actually just a data frame library, which implements the Apache Arrow standard, and we'll get a little bit more onto that later. So to extract data, we first need a node, so because that's where our data comes from. So here's some interesting statistics. To sync an archival node on Ref, it would take around 50 hours and take you roughly 1.92 terabytes. So this is a few months out, but so I would say they're around 2 terabytes right now. On Aragon, it will take you around 5 days or 2.2 terabytes. On Geth, it will take you 1+ months and 14.5 terabytes. And Nethermind, it will take you 1+ months and also around 14.5 terabytes. So I guess you might ask, like, why the discrepancies? Like, why does it take such a big delta to sync archival? When I say archival, I mean everything from block 0 all the way to the latest block. Why does it take 50 hours? In fact, there are snapshots for Ref right now, which reduces that down to 6. So if you spin up a fresh machine, you can actually get an archival node in less than 6 hours. And you might ask, like, why is there so much discrepancy? So the reason is because Ref actually uses a new kind of database technology, MDBX or something, developed by a Russian guy, single Russian guy, by the way, that is supposedly a lot more performance than Levels DB, which is what Geth and what I think Nethermind uses, which is why we can now store a archival node under 2 terabytes, which is really amazing. So a little bit of disclaimer here, Ref is actually heavily inspired by Aragon, and if you look through the source code, you can actually see a lot of its inspirations and where it comes from. And here are some acknowledgements. So Ref, blah, 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 like, has a lot of inspirations from Geth, Aragon, Akula, especially MDBX. But yeah, anyway, what the point I'm trying to make is that it is possible to run an archival Ethereum node on consumer laptops now. So back then, if you wanted to run a archival node of Geth or Aragon, that would take you 15 terabytes. But now with Ref and Aragon, it takes you maybe 3-4 terabytes, which is pushing it, but it's still very doable, you know. And data is the new oil, right? We live in the information age, and like oil, data is valuable, but it's useless if it's unrefined. So we'll explore, now that we've explored how to extract the data and how to get your oil, we'll explore how to refine the oil. Anyway, archival nodes are basically the equivalent of modern day oil reserves. And what's cool about data analysis is that everyone's on a level playing field, because no one's controlling some kind of secret data. The data is open out there for everyone to analyze and extrapolate. So here's what a standard refinement process could look like. You have your archival node, Ref, and then you would extract that out into local files or into your cloud buckets via some kind of format. Historically, this would be like a CSV, and you would maybe use something like ETH to CSV, which is a tool. to extract the data from your node into your local files and upload it to the cloud. And then you would kind of do some kind of transformation. Is the mouse working? Yep. Do some kind of transformation here via maybe something custom or maybe something standard, and then you would present the query results here. So there's ref, there's pocket and delta. If you don't know what that means, don't worry, we'll go through it later. And then there's your query results. So what I want to talk about today is these three things: Cairo, the local files, and Polis. So let's say hypothetically you got your ref node set up, and you're ready to extract data. So what do? I would turn to Cairo. Cairo's again a tool from Paradigm, which is used to extract data into the Parquet format. And if you were like me 3 months ago and I didn't know what Parquet was, I went to ChatGPT and I kind of asked it to explain what it is in the context that I cared about. But basically, Parquet is just a data format. It can be like CSV, it can be a JSON. Parquet is just a more efficient way to store data and a more efficient way to store, read, and transform data. And it's also open source. There's a standard behind it. I think it's like Apache Arrows, if I'm not mistaken, and a lot of real-time time series data, especially financial data, uses the Apache Arrow standard, so it's battle-tested and scalable. Yeah, so this is just like a brief overview of the differences between CSV, JSON, Parquet, and Avro, which I've never heard before until I put this picture in. But yeah, so Parquet fulfills a lot of criteria. It's compressible, it's splittable, it supports complex data structures. For example, binary or even bytes. It supports strings. It supports lists of strings. But the only downside is that it's not human readable. So if you don't have any tooling to help you with, or if you're not familiar with computers, your typical R boys or your typical data scientists who can only read stuff from Excel, Parquet might be a bit cumbersome or tedious. But since we're all computer experts here, this shouldn't be an issue. So let's continue. And I notice you might have noticed that I've mentioned Rust many times. It sounds like I'm a fanboy, even though I am more of a Haskell fanboy. That's unrelated. Even though these tools are Rust related, if you are more inclined to use it in another library, for example Python, don't worry, there are Python libraries and wrappers available. This is my favorite image. The Python baby boy gets, gets his aid from the Rust soldier who's returned from the battlefield. Anyway, so this is how we can use Cairo. So this is the API for Cairo, and I think this is like a month or two outdated, and Cairo might have updated since. But using Cairo, you can extract a bunch of data sets, a predefined data sets, I will add, from your Ethereum node. So you could do things like you could hypothetically extract out logs from a certain range of blocks. So you would type Cairo logs into your terminal, -B, and you would put in like 16 mil to 17 mil blocks. So you extract out all these logs into like a Parquet file. Or if you're more inclined to extract out the block data, for example, the author of the block, the base fee of the block, the block number, the block hash, and so on. You can also do that through the blocks data set. And there are actually a lot more other data sets, predefined data sets that I will add, such as transactions, storage differences, where you can find out the slots, and slot differences, where you can find out the slot deltas for each contract, events, which is just logs, and bounds differences, which tells you the Ethereum bounds delta for each block. But anyway, this is how you would use Cairo dataset, and some other parameters. So let's say hypothetically that we've used Cairo and we've extracted out these datasets to our file. Like, how can we make sense of it? How can we use it? Well, how I would use it is I would read it in Python, because I find it a lot more easier to perform complex data transformations with. So how you could read it is you could import Polis and read it using the library. But this is very tedious, right? You need to open up your Python interpreter. So that's like one command. You need to import the library, which is another command. And then you also need to type out PL, which is Polar's read packet, and enter the file name, which is also very tedious if you're not in the correct directory. So that's like 3 to 4 commands just to read a file. So tedious. So it's just not very, I would say, not very reasonable, not very practical for your average data scientist, Joe. But luckily, we're all Linux experts, or to some extent, computer experts, and you realize, hey, I could just alias this into some kind of command. And luckily for us, not Storm at not Storm from Twitter mentioned that, hey, why don't you just alias this command ppq, and then now instead of typing out 4 commands, all you do is type out ppq and your file name, and then you can read the data frame like that in a jiffy. So yeah, this is like little things that actually make exploring the data a lot more effortless, which when exploring data is made more effortless, you will explore it more frequently, and then you will find a lot more relations or correlations. That's what I've personally found. Reduce the barrier of entry, reduce the friction required, and you will find yourself doing a lot more of these tasks. But anyway, so we have the data in a Pocket format, and now we want to do some kind of transformations to it. For those of you who are familiar with pandas, this syntax might be a little bit different because I think like Pandas' API has kind of evolved over the years, but Polar's is a pretty new one, and it has actually learned a lot from what Pandas would consider good. A lot of the API is very clean, very composable, and very consumer friendly. So this is an example of how, let's say I wanted to find which addresses would send out the most transactions in a given a given chunk of block. So I would group everything by the addresses, the to address, and I would aggregate things by the transaction hash. So pl.co transaction hash .explode just means I want to convert, when I group everything by this address, I want to group everything and accumulate it into a list. And after accumulating it into a list, as you can see here, in transaction hash is a list of binary data. I also want to count the number of times this transaction has been sent, has received, this address has received a transaction. And then we can just do a .count, and we can alias it. So this is like 3 lines of code, and you've managed to figure out the most frequently sent addresses in Ethereum from a certain block range, which is pretty cool in my opinion, because if you were to do this for JSON RPC, where you have to manually query each block data, like doing 1,000 blocks would take you maybe 10 to 15 minutes. This took me less than like 10 milliseconds. So when you're doing like chunks of historical data, this is where this method really shines. You can do more complex analysis with Polar's via its APIs, but you have to go in and kind of discover it for yourself. The API library is quite verbose and quite rich, so it might seem a bit intimidating, but I highly encourage you to start off with like a project to kind of check things out. For example, here we're checking out the intersection of addresses, like which addresses would send to other addresses, which is quite interesting if you're looking at from a forensics perspective, because you might want to say, okay, what addresses might send transactions at a similar time interval? You could definitely do this with a one-liner in Pocket, which is not this, by the way, but you could definitely do that through like some kind of between time interval thing. And this is done in chunks of data. And Polars has been shown to be able to transform over like a million rows in less than like a second. If you were to do that via JSON RPC, or if you do it via CSV, it could take a lot longer. But yeah, anyway, TLDR, Cairo, pretty easy to use, very, very open source and extendable. In fact, I've also extended it a little bit by writing out a custom data set that extracts out the pricing data. So in this case, for example, if I wanted to get the price of ETH BTC or ETH USDC or ETH DAI, I can write out like a custom contract to do so via the ETH call data set. Yep. So we'll speak through this a little bit, but TLDR is that you can write arbitrary code for data retrieval without the contract deployment, and how you do that is by abusing the ETH call opcode. The ETH call JSON RPC code. So this works by returning data in the constructor, because usually you don't return data in the constructor in Solidity. You can't do that because why do you want to return data in the constructor? It's useless. But for our use case, where you just want to optimistically deploy a contract and get its return data. And extract the data into Polis, you can definitely do so. So we could create a contract like prices, which is a UN256, a list of numbers. We get the price for, say, the index, and then we encode it into this ABI encoding scheme and return the data. You have to go into some assembly fuck around, but that's the price you pay for wanting things to be clean, I suppose. But yeah, so this is how you would abuse the ETH call opcode, and I actually have a whole repository dedicated for that if you're interested. But yeah, you can just easily extract and organize data in an ad hoc manner. Maybe I'll call this JIT, just-in-time data. But yeah, TLDR, running a bit short on time. With Ref, we can now extract. We now have the raw data, and with Cairo, we can extract the raw data very efficiently and store them locally or in the cloud, and then we can use Polis to refine them. And so that's the structure that I found to be working really well for me. Thank you very much.